On a dark mountain in northern Chile, at an altitude where the air is thin and the sky is almost impossibly clear, a machine the size of a small car opened its eye and looked at the universe in a way no instrument ever had before. What it saw in the first few hours of operation stopped astronomers in their tracks. Not because it found something impossible, not because it detected an alien signal or a rogue planet on a collision course with Earth, but because it proved, in a single breathtaking release of images, that humanity now possesses a tool capable of rewriting the rulebook of modern astronomy. This is the story of the Vera C. Rubin Observatory, and why its latest images have left even the most experienced scientists on the planet stunned. The observatory sits atop Cerro Pachón, a peak chosen with surgical precision for its still air, its dry climate, and its almost total isolation from artificial light. It is an 18-story facility built at a cost of roughly $810 million, funded jointly by the United States National Science Foundation and the Department of Energy's Office of Science. It is named after Vera Cooper Rubin, the astronomer whose meticulous measurements of galaxy rotation in the 20th century provided some of the first compelling evidence that most of the matter in the universe is invisible to us, a mystery we now call dark matter. It is a fitting name because the machine built in her honor may finally give scientists the data they need to understand what she first glimpsed decades ago. For years, this project existed largely on paper in inside engineering labs, known to insiders simply as the Large Synoptic Survey Telescope, before it was formally renamed in honor of Rubin. Its construction spanned more than a decade, delayed and refined repeatedly as engineers worked to solve problems that no observatory had ever needed to solve before. Because nothing built at this scale, with this particular combination of speed, sensitivity, and field of view, had ever been attempted. When the finished camera was finally lifted onto the telescope structure atop Cerro Pachón in the early months of last year, it marked the culmination of a project that had consumed the careers of entire generations of engineers, physicists, and astronomers. Officials who oversaw the effort described it as proof that ambitious, large-scale basic science remains achievable when national institutions commit to a long-term vision rather than a quick result, a sentiment echoed across the scientific community when the first images were finally revealed to the public. At the heart of the observatory sits the Simony Survey Telescope, an 8.4-meter giant paired with the LSST camera, the largest digital camera ever constructed. To call it large almost undersells what it actually is. The camera weighs around 3 tons, roughly the mass of a fully loaded pickup truck. Yet it is engineered with a precision that allows it to capture images of 3,200 megapixels, a resolution so extreme that it would take hundreds of modern smartphone screens arranged together just to display one image at full size. Built and assembled at the SLAC National Accelerator Laboratory, the camera is made up of 189 individual sensor chips, fused into a single seamless imaging surface. Every 40 seconds, through the long Chilean night, it captures a brand new frame of the sky, cycling through target after target with a rhythm that never stops. To engineers who worked on the project, the camera itself is almost as remarkable a story as anything it has photographed. Each of its individual exposures produces a file roughly 8 gigabytes in size, and across a single clear night atop Cerro Pachón, the observatory can generate somewhere in the neighborhood of 1,000 such images, translating into around 10 terabytes of fresh data before sunrise. Multiply that across the full 10 years of the planned survey, and the observatory is expected to capture something close to 8 million individual images over the life of the mission, forming an unbroken visual record of the changing sky on a scale that had previously existed only in the imagination of astronomers. Every one of those frames must be processed, calibrated, and compared against previous observations within minutes, an engineering challenge nearly as demanding as building the camera itself, requiring a global network of computing centers working in near real time to keep pace with the flood of information pouring down from the mountain each night. When the first images were finally unveiled to the public, the reaction was immediate and visceral. One of the earliest released views showed the Virgo cluster, a dense gathering of galaxies relatively close to our own Milky Way in cosmic terms. In that single frame, astronomers could see an extraordinary range of objects all at once. Bright foreground stars glowing in shades from hot blue to cool red, nearby blue spiral galaxies caught mid-rotation, and far more distant red galaxy groups fading into the depths of the observable universe. It was, in the words of scientists who study these fields for a living, a demonstration of just how much scientific range a single Rubin image could contain. Another early release combined nearly 700 separate exposures, taken over just 7 hours of observing time, and when stacked together, it revealed faint clouds of gas and dust belonging to the Trifid Nebula, the Lagoon Nebula, structures thousands of light years from Earth that had never been rendered in this kind of layered, luminous detail before. Perhaps the single image that best captured the public imagination showed roughly 10 million galaxies in one frame, and even that staggering number represented only about 1/20th of 1% of the nearly 20 billion galaxies the observatory expects to catalog over the coming decade. Scientists who had spent entire careers studying small patches of sky in painstaking detail were suddenly looking at a single image containing more galaxies than most surveys had documented in years. It is difficult to overstate what that moment felt like inside the research community. This was not an incremental improvement over previous telescopes. It was a leap into an entirely different scale of observation. What makes Rubin so different from earlier great observatories is not simply its size or its resolution, though both are extraordinary. It is the way it observes. Traditional telescopes, even famous ones like Hubble or the James Webb Space Telescope, tend to stare deeply and patiently at a single, narrow patch of sky, gathering every possible photon from one small region over long stretches of time. Rubin does something fundamentally different. It sweeps. Across the coming decade, it will scan almost the entire visible southern sky, returning to the same patches of space again and again, roughly 800 times over 10 years, building what scientists have started calling the greatest cosmic movie ever made. Each night it produces around 10 terabytes of raw data and generates as many as 7 million individual alerts flagging anything in the sky that has changed since the last time that patch was observed, whether that is a flickering variable star, an asteroid drifting through the frame, or the sudden brilliant flash of a dying star tearing itself apart in a supernova explosion. This is the true power hidden inside Rubin's design, and it is the reason its latest images have generated so much excitement among professional astronomers rather than simple public curiosity. A telescope that can repeatedly photograph almost an entire hemisphere of sky night after night, year after year, is not just a camera. It is a change detector operating at a planetary scale. It can catch objects and events that would otherwise vanish unnoticed between the rare visits of other instruments. Somewhere in that endless stream of changing pixels lies the potential to catch a supernova within hours of its first flicker of light, to watch a black hole suddenly begin devouring nearby gas and dust, or to notice a faint moving point of light that turns out to be a previously unknown object drifting through our own solar system. And Rubin has already begun proving that potential in dramatic fashion. During roughly 6 weeks of early optimization observations, before the full 10-year survey had even formally begun, the telescope discovered more than 11,000 previously unseen asteroids. Among that haul were 33 near-Earth objects, space rocks whose orbits bring them into the neighborhood of our own planet, and 380 trans-Neptunian objects, icy bodies drifting in the frozen outer reaches of the solar system far beyond the orbit of Neptune. To put that number in context, it took the entire astronomical community, using every other ground-based survey, combined many years to build up asteroid catalogs of similar size. Rubin achieved a meaningful fraction of that in a matter of weeks, almost as a byproduct of simply testing its systems. Astronomers who track near-Earth objects for planetary defense purposes, the small but very real possibility that a large asteroid could one day threaten Earth, immediately recognized what this meant. A machine capable of finding this many new objects this quickly, once running at full operational capacity for a full decade, is expected to detect the vast majority of large asteroids in the inner solar system that remain undiscovered today. Some of those early discoveries had already been building even before the official survey began. A handful of asteroids were first spotted during commissioning tests using an earlier prototype camera in the closing months of the previous year, followed by more than 1,000 additional detections during the dramatic first look phase when the finished camera returned its earliest public images. But it was the 6-week stretch of full-scale optimization testing that produced the overwhelming majority of the haul, more than 11,000 new objects in total, a number so large that mission scientists were quick to reassure the public that nothing in the newly expanded catalog posed any threat to Earth. As one of the project's lead scientists put it at the time, there were no surprises among the new detections, only confirmation that the solar system contains far more small, previously hidden objects than earlier, less capable surveys had ever been able to reveal. This is where the deeper story of Rubin's importance begins to unfold, because the sheer scale of what it is capturing forces scientists to confront just how much of the universe still remains functionally invisible to us. Vera Rubin herself spent much of her career studying the rotation of galaxies, and she found something that did not make sense according to the physics of the time. Stars at the outer edges of spiral galaxies were moving far too fast. According to the gravity generated by all the visible matter in those galaxies, stars that far out should have been flying off into intergalactic space entirely, yet they remained bound in orbit. The only explanation that fit the data was that an enormous amount of additional invisible matter must be present, exerting gravitational pull without emitting any light of its own. This became one of the most important pieces of evidence for the existence of dark matter, a substance that appears to make up roughly a quarter of the entire universe, yet has never been directly detected or explained. The observatory named in her honor is now positioned to attack that mystery with a scale of data collection that simply did not exist before. By repeatedly imaging billions of galaxies across the full span of the observable sky, and by measuring subtle patterns in how the light from distant galaxies is bent and distorted by the gravity of matter lying between them and Earth, a phenomenon called gravitational lensing, scientists hope to map the distribution of dark matter across huge volumes of the cosmos with unprecedented precision. At the same time, Rubin's data will feed directly into the study of dark energy, the mysterious force that appears to be accelerating the expansion of the universe itself. Together, these two invisible components are believed to make up around 95% of everything in existence, meaning the ordinary matter that makes up stars, planets, and people is little more than a faint trace floating in a cosmos dominated by forces we still cannot directly see or fully explain. Cosmologists working on the dark energy science collaboration, many of whom spent years preparing for exactly this moment, using earlier, smaller surveys as a testing ground, have described Rubin as the instrument they have effectively been waiting their entire careers to use, a machine finally capable of gathering data at the scale their theories require, in order to be properly tested against reality, rather than simply refined on paper. What makes this moment feel different from previous efforts to study dark matter and dark energy is the sheer volume and consistency of the data Rubin is producing. Previous surveys often had to stitch together observations, taken with different instruments, at different times, under different conditions, introducing subtle inconsistencies that made precise measurements difficult. Rubin removes much of that uncertainty by using a single instrument, observing under a single consistent strategy, repeatedly, for 10 uninterrupted years. When the full legacy survey of space and time is complete, its dataset is expected to include tens of billions of individual cosmic objects, and something on the order of 30 trillion individual measurements of their properties, brightness, position, color, and movement over time. It will become, almost immediately upon completion, the single largest and most comprehensive catalog of the universe ever assembled by human beings. And unlike some previous large-scale projects, this dataset will be made openly available not just to professional astronomers around the world, but to the general public as well, opening the door to citizen science projects where amateur enthusiasts can help sift through the flood of data for interesting discoveries. When the very first images were unveiled, the release was not treated as a quiet technical milestone confined to academic journals. It was staged as a global celebration with an event held in Washington, D.C., and hundreds of public watch parties organized in cities and universities around the world, each one drawing crowds eager to see the pictures the moment they went live. Planetariums, science museums, and university auditoriums filled with people who had no formal background in astronomy at all, simply drawn by the promise of seeing the universe rendered in a way it had never been shown before. That reaction mattered because it signaled something beyond the purely scientific value of the images. It showed that Rubin had captured the public imagination in the same way earlier landmark achievements in space exploration once did, at a moment when many assumed the age of headline-grabbing astronomy discoveries belonged mostly to the past. It is worth pausing here to appreciate just how much of a shift in scientific culture this represents. For most of the history of astronomy, discovery belonged to whoever had access to the largest telescope and the most observing time. Rubin, by design, inverts that model, because it observes almost the entire sky rather than a single fixed target, and because its data becomes public, a student with an internet connection and some curiosity could, in principle, discover something in Rubin's data that no professional researcher has yet noticed. Astronomers involved with the project have spoken openly about hoping to find what they call unknown unknowns, phenomena so unexpected that nobody currently studying the sky even knows to look for them. This is part of why the release of the latest images generated such a strong reaction across the scientific community. It was not just the beauty of the pictures, it was the realization that this machine is now actively scanning the sky for the unexpected every single night, and has been doing so with remarkable consistency since its full survey operations formally began. The observatory has also introduced a real-time alert system that represents a genuine milestone in observational astronomy. Within moments of detecting a change in the sky, whether that is the sudden brightening of a variable star, the telltale signature of a supernova beginning to explode, or a faint point of light moving against the background stars in a way that suggests a new asteroid or comet, Rubin can automatically flag that event and alert astronomers around the world so that other telescopes can immediately turn their attention to the same spot before the phenomenon fades or changes. This rapid monitoring capability is expected to play a critical role in what scientists call multi-messenger astronomy, the practice of studying a single cosmic event using multiple types of signals at once, combining traditional light-based observations with data from gravitational wave detectors and high-energy particle observatories. When two neutron stars collide, for example, they release a burst of light, a shower of gravitational waves rippling through space-time, and potentially high-energy particles, all within a narrow window of time. Catching all of these signals together gives scientists a far richer picture of what actually happened than any single method could provide on its own. And Rubin's ability to almost instantly notice something has changed in a given patch of sky makes it an essential first responder in this global network of instruments working together. None of this happened by accident or overnight. The road to this moment stretched back many years, through the construction of the observatory itself, the painstaking assembly of the camera at SLAC, its installation atop the telescope, and then months of careful calibration and testing before the observatory's leadership judged the system ready to formally begin its 10-year survey. That decision, according to the scientists overseeing the project, was based on a careful review of technical readiness across several dimensions, including the sharpness of the images being produced, how quickly and efficiently the telescope could survey large areas of sky, how reliably the entire system could operate night after night without interruption, and how accurately its instruments were calibrated against known reference points in the sky. Only once all of these benchmarks were satisfied did the observatory transition from a period of testing and optimization into full operational science, a threshold it crossed only very recently, meaning the images now stunning scientists around the world represent not the observatory's peak performance years from now, but merely its opening moves. That fact alone should give a sense of what lies ahead. If a handful of weeks of early testing were enough to uncover more than 11,000 new asteroids and produce imagery detailed enough to leave veteran astronomers audibly startled, then the full decade-long survey, running continuously, systematically, and consistently across the entire visible southern sky, promises to reshape entire fields of astronomy. Scientists studying the outer solar system expect Rubin to eventually catalog the vast majority of large trans-Neptunian objects, potentially settling long-running debates about the structure and history of our solar system's distant frontier. Researchers studying stellar explosions expect to catch supernovae earlier and more frequently than ever before, potentially observing the very earliest moments of these violent events in a level of detail that has simply never been available. Cosmologists, hoping to finally pin down the true nature of dark matter and dark energy, now have access to a dataset large enough and precise enough to test theories that have remained frustratingly unresolved for decades. And yet, for all the very real, very concrete achievements already on the record, the deeper excitement running through the scientific community has less to do with the specific discoveries made so far, and more to do with what remains completely unknown. Every time astronomers have built a fundamentally new way of observing the universe, from the first optical telescopes to radio astronomy to space-based observatories, the universe has responded with surprises nobody predicted in advance. Pulsars, gamma-ray bursts, the accelerating expansion of the cosmos itself, none of these were things scientists set out looking for. They were discovered because someone built an instrument capable of noticing something strange, something that did not fit the existing picture. Rubin, by its very design, is built to notice exactly that kind of anomaly, sweeping continuously across nearly the entire sky, alert to any flicker, any movement, any unexpected change. Somewhere within the billions of galaxies Rubin will observe over the coming decade, somewhere within the trillions of individual measurements it will collect, there may be a discovery waiting that no scientist currently studying the cosmos has predicted or even imagined. It might be an entirely new class of cosmic explosion. It might be direct evidence of the true nature of dark matter, finally settling a question first raised by the very astronomer this observatory is named after. It might be something else entirely, something that does not yet have a name, because nobody has ever had the tools to see it before. What is certain is that scientists around the world are no longer simply waiting to find out. Night after night, image after image, the Vera C. Rubin Observatory is already watching. And for the first time in the history of astronomy, an entire hemisphere of the sky is being filmed continuously in real time for exactly this reason. The latest images have stunned scientists, not because they revealed the impossible, but because they proved, unmistakably, that the machine capable of finding it has finally truly begun its work.